let's get started then. So the information on page 6 was talking about a chemical reaction. How do we know when a chemical reaction, or it's talked about, how do we know when a chemical reaction has occurred?
When a new substance has been formed.
Yep, so we've formed a new substance. Now sometimes they're easy to see and sometimes they're hard. This is where a chemical equation is going to help us out. And when we think about chemistry and reactions, so if I was to write it out in very general terms, I would have reactants forming products. So in this case, my product is my new substance, isn't it? So I've combined something together in the right conditions for them to react chemically, and I've produced something new. And there are two ways of looking at chemical reactions. There is quantitative and qualitative observations. Do you know what either of those words mean?
I think quantitative is more looking at the actual changes in mass and actually quantifying what has happened, whereas qualitative is sort of observing the changes that have happened.
Yeah, so I like to simplify quantitative, how much? That's asking, about, well, how much? How much of this do I need to react to form, if I want 10 grams of this, how much do I need of my reactants? So qualitative then is, what are we doing there? So quantitative, yes we do, and we're definitely measuring how much. And Jarek is right. One of the ways that we measure in chemistry would be measuring in grams. But what's qualitative? Qualitative is basically, what do I see? Okay, all I want to know is, just like when you did the precipitation reaction experiments and you were combining two reagents together and you were just looking to see if a precipitate formed. So that was a qualitative observation because you weren't measuring how much. It was just, did a reaction happen, yes or no, kind of thing. So that's what we've done so far has all been qualitative, hasn't it? Because we haven't been worried about how much. But we are going to be worrying about how much from now on. And that's why we're going to be doing some calculations as we progress. So, some of the ways that we know that a chemical reaction has occurred, actually on page 7, it's talking about physical changes, so that we know the difference what's involved in a physical change then?
It's like a change of state, so when ice melts to water.
Yep, changing states. That's right. So do you know, what's the chemical formula for ice?
H2.
That's why it's a physical change. Because we have not altered the chemistry of it at all, have we? What's another physical change? Well, if we look in the booklet, we can change the size of the lump. We can take a big lump and we can cut it into smaller pieces. So,
Change of appearance.
sorry?
It's a change of appearance.
Change of appearance. Yes, that's right. Change of appearance. So, you know, like if we've got a big lump of ice, or we've got ice blocks, or we've got ice chips, they're all ice, aren't they? And so all we've done then is cut them up into smaller pieces. If we dissolve a solid in a liquid, for example, sugar in water, that is a physical change. And this is not the case of dissolving salt in that. Well, because what we're really doing something different when we dissolve salts in water than when we dissolve sugar in water. Sugar is a molecule, and when it sort of falls apart in water. Not the molecule, but the bonds holding each molecule together. Whereas with our ions, they are attracted to the water in a different way. And then we can separate mixtures. We can't separate something that's chemically bonded. So that's another way of determining whether it is a physical, they're just physically bound together, or if it's a chemical bond. All right, and so here what we're talking about is just all to do with energy in this one. So our gases have more energy than our liquids, and our liquids have more energy than our solids. So we can add or remove energy from the system to change states. Okay, now, whereas with a chemical change, what we have to do is we have to break chemical bonds in the reactants, and then we form new bonds in products. That is what we must have for a chemical reaction. Now we have the law of conservation of mass for chemistry. And what that tells me is that if I start with, if I have 2x plus 3y plus z on my reactant side, then I must end up with the same. How about, I'll do it differently. I'll say, 2xy plus z. Plus, no, we'll go 8b, 3ab. No. It would be easier if I just did a chemical equation. Let's don't take the numbers away. Let's just assume then that it doesn't matter what they are. All we've done is we've rearranged them, but I have the same number of them. I have to have the same number. That's what the law of conservation of mass tells me, is that whatever I have over here, doesn't matter how it's chemically bonded to something else, but if I've got element X here, I have to end up with element X over here too, as a product. Element A must be here as element A for a chemical reaction. We're not changing the elements. All we're doing is we're taking the elements that are bonded in one particular way and we're reacting them so that they are now bonded in a different way. Okay. We cannot create extra atoms and we don't destroy any atoms either. Now, the area where we're talking, we do end up with a change in mass is in nuclear decay, but this is not a nuclear reaction, this is a chemical reaction. Okay, now we talked about chemical equations being reactants to products, and if we look then at an example of our law of conservation of mass, if we're writing this equation where we're reacting phosphorus and chlorine gas. So in this case, it's just phosphorus, the element, and chlorine gas. It's important that we remember that our halogens, all of group 17, are all diatomic. So they exist in nature bonded as two atoms bonded together. The same as oxygen is O2, nitrogen is N2, hydrogen is H2. All of those are diatomic molecules of the gases. So if I'm reacting chlorine gas, then it has to be Cl2. And we're told that the product is phosphorus trichloride. What can you tell me, if I say the name is phosphorus trichloride, what kind of bonding must it have? Covalent, why?
Because it's between two molecules.
It's between no. But what is it in the name that tells you that it must be covalent?
Does it have something to do with the number of bonds?
No, I'm talking just about the word.
Because it says it's trichloride.
Yeah, it said trichloride. Trichloride, instantly, covalent bonding. Because we don't say how many things are present in ionic bonding. Okay, so you would know then straight away that this must be a non-metal and this is a non-metal. So just trying to remind you back from Criterion 7. Now this is not balanced, is it? What do we need to do to balance it? Because what this is telling me is at the moment I have one phosphorus and I have 3 chlorines. If I look at the 3 and the 2, I'm looking for
You want 3 of the phosphorus trichloride. No, 2, sorry. 2 of them and then 3 of the chlorine, and then just 2 of the phosphorus.
yeah. So we're looking for something that that has these as its factors, aren't we? And that whiteboard marker seems to be pretty well dead now. So what we do with it when we balance a chemical equation, it has to be with the big number at the front, which we would call a coefficient. We can't change the little numbers down the bottom here because if we change them, we change the substance. And we can't do that because then we would be changing the reaction. So we need to leave these little numbers, the subscripts, the same, and we balance with the big number up the front. Okay. And then we should include states if we know what our... So we were told it was a solid, this is a gas, and this is actually a liquid. So if you look on page 10, here is another example of working through a chemical equation. We're reacting hydrogen gas. So remember that hydrogen gas is diatomic. and we're reacting it with chlorine gas, which is also diatomic, and it's producing hydrogen chloride gas. Now we weren't told any prefix, any numbering, so there's only one of each. And so we need to go through and balance this with a coefficient. If I've got 2 hydrogens here and I've got 2 chlorines here, then I'm going to need to put a big 2 out the front to say I need 2 of them. If you look at the picture, it's a little bit faint, but you can see the picture on page 10 shows you the diatomic hydrogen as the 2 little spheres joined together. So that's a bond, a chemical bond there. And the same with the chlorine, there's a chemical bond there. And in the process of this chemical reaction, those bonds are broken and we form these new bonds. And the big 2 out the front tells me that there are 2 of them. Okay, now on page 11 we have a worked example, and this is a decomposition reaction. You don't need to know that it's a decomposition, but what happens here is that if you heat it up, it's going to fall apart. So let's have a look at it. Process involved in this. Now firstly, we've got copper nitrate. Ooh, that's not nitrate. So there's a 3 missing off the NO there. If you can just stick that all in there, that'd be great, thank you. So copper nitrate, we're forming copper oxide and nitrogen dioxide and oxygen gas. Now we're going to start the balance, to balance our equation. And it's easiest if we look to see if something only occurs in one place. And so that would be, so we're not going to start with the oxygens because the oxygen is in all 3 of our products. So we start with the copper and the nitrogen. If I look at the copper, then there's 1 to 1 at the moment. But I can see that if I've got 2 nitrate ions, I'm going to need 2 of these, aren't I? So I'm going to put a 2 there and just see what happens as I go along. So now I'm up to balancing the oxygens because the coppers and the nitrogens are balanced. I've got 2 oxygens in each of these nitrogen dioxides, but I've got 2 of them, so that's 4 oxygens altogether. I've got 2 oxygens in here, and I've got one oxygen here. So that is a total of 7 oxygens, which is not balanced. There is it. So what we need to look at is, well, how are we going to increase the numbers of oxygens on our reactant side? We need a big 2 out the front. Yeah? Now we've done that, it changes these as well. So I'm going to need to come back and put a 4 here, because I've now got 4 nitrogens, and 2 here, because I've now got 2 coppers. And now I'm going to look and see what's happening with my oxygens. If I add up all my oxygens, 3 times 2 is 6, times 2 is 12. Isn't it? 12, and then 4, I've got 2 times that is 8, and I've got 2 here, and I've got 2 here, and that equals 12 oxygens, and so now it's balanced. So sometimes with balancing equations, you do need to go backwards and forwards as you work out how much of each you need for balancing. And then lastly, we go through and put in states. So that was a solid, a gas, and a gas. Okay, so there is a, try it yourself, and there are some questions then. And there's